Hi guys, in this lecture I am taking lecture on the topic complex analysis 1, in which in the previous lectures I started analytic function. In last lectures I introduced analytic function, and then I was discussing about the properties of analytic function. Up to the last lecture I discussed first thing, that is analytic function, in which I told you about definition of analytic function in two ways. One is analytic function at a point, another is analytic function in a domain. At a point, I told you a function is said to be analytic at a point if it is differentiable not only at that point but also in the neighborhood of that point. And second, I define analytic function in a domain as a function is analytic in a domain D if it is differentiable at all the points of the domain D. And I also told you that there are two other names of the analytic function. One is holomorphic function, another is regular function. Then I told you what is the necessary and sufficient conditions for a function to be analytic. And in which I told about CR equations. CR equations means Cauchy-Reimann equations. Then I told you if we take a function fz equal to u plus iv, where you know that z is an ordered pair of xy, so u is also function of xy, v is also function of xy, then this is analytic if and only if their partial derivative of real and imaginary part del u by del x equal to del v by del y and del u by del y equal to 9 minus del v by del x. This is the necessary and sufficient condition for which we can check any function is analytic or not mathematically. Up to the last lecture, I discussed these things, and also I took up some examples on the analytic functions. If we have sums, we have the numerical questions, then how you can check whether given function is analytic or not. Now, in this lecture, first I will take up the another form of analytic function, another form of CR equations, because you know that here this complex function, depending upon this complex number z equal to x plus iy, and that is a Cartesian form of the complex number. Here you know that x is the real part and y is the imaginary part. And I have already told you in just our introductory lecture that if we put x equal to r cos theta and y equal to r sin theta, we get another form of a complex number, that is r times r cos theta plus I sin theta, and this is polar form. So in this lecture, first I discuss what is the polar form of the CR equations. If in any numerical questions, in any sum, there is given a function into polar form, then how you can check the analyticity of the function. So first I discussed what is the form of CR equations. First, polar form of CR equations. If we take function fz equal to u plus iv. Now here z, we are taking z is r cos theta plus r sin theta. That means it can be represented r equal to e to power I theta, because you know that by Euler's formula cos theta plus I theta can be represented in exponential form e to power I theta. And also you know that r equal to modulus of z, that is x square plus y square, theta equal to tan inverse y upon x. This is basic transformation of Cartesian form into polar form. You know that. Then what is the CR equation? So here in polar form, CR equation means Cauchy-Reimann equations are, if we take z equal to r a I theta, then Cauchy equation del u by del r equal to 1 upon r del theta del v by del theta and del u by del theta equal to del v by del r. Sorry. Del v by del r equal to minus 1 upon r del u by del theta. These are the polar form of CR equation. Means if any question is given into the polar form, means complex function is given into the polar function, and you have to check the analyticity of that function, then you can check this by using this form of CR equation. As here also we can take an example. If we take an example, find the value of p such that fz equal to u plus iv equal to f of r e I theta, means function is in polar form. Fz is this, as fz is equal to r square cos 2 theta plus I times r square sine p theta is analytic. If this is the sum, if polar equation is this is real part, this is the imaginary part, then what is the value of this p such that given function is analytic? So here, if we compare this by our standard form of complex function fz equal to u plus iv, so here u equal to r square cos 2 theta and v equal to r square sine p theta. And we know that CR equation, these are the CR equations. These are CR equations. Now, here we have to check the analyticity of the function by using CR equation. So we have to calculate the partial derivative of these two real and imaginary parts with respect to r and invisible theta. So first we calculate del u by del theta. Del u by del theta is minus r square 2 sine 2 theta. Del u by del r is 2r cos 2 theta. And del v by del r, and also find the partial derivative of v. Then del v by del r is 2r sine p theta, and del v by del theta is r square p times cos p theta. These are the partial derivatives. And now, if function is analytic, then these must be satisfied CR equations. Since fz is analytic, so u and v satisfy CR equations. CR equations means del u by del r equal to 1 by r del v by del theta. Here del u by del r del u by del r is 2r cos 2 theta. Del 1 upon r is 1 upon r. Del v by del theta is minus r square 2 sine 2 theta. That is del u by del r equal to del v by del theta. Then del v by del theta is, del v by del theta is 1 upon r, that is r square p cos p theta, right? R is cancelled out. If you compare it, we get p equal to 2. That is your answer. That is the value of p if given function is analytic. And this is the method to check the analyticity if given complex function is in polar form. Now, analytic function, I've discussed the theory of analytic function. Now I completed basic theory, basic concept of analytic function, and I took up number of examples, number of numerical questions by which you can follow this thing. And now here I am taking last example because in introductory lecture I told you what is the limit of the complex function, what is the continuity of the complex function, what is the differentiability of continuity function, and in each case we see that the function is of two variables. So method to check the differentiability, continuity, and existence of limit is slightly changed as compared to the function of single variable. So we taking an example in which you have to use the concept of check of the differentiability of function of two variables. That is very important example by which you can understand how you can check the existence of limit, continuity, and differentiability of the function, and then analyticity of the function. Question is, show that function fz equal to u plus iv, where fz equal to s cube 1 plus I minus y cube 1 minus I upon x square plus y square, when z is not equal to 0. This is equal to 0 when z equal to 0, satisfies CR equations at z equal to 0. Question is the function analytic at z equal to 0? Justify your answer. This is a function of two variables in complex form, in Cartesian form, and first you have to show that this function satisfies CR equation at particular point z equal to 0, and then question is, okay, function is analytic at z equal to 0. Although I have defined analytic function at a point, and I told you a function is differentiable at a point and also differentiable in the neighborhood of that point, then we say that function is analytic at that point. So here we have to use this definition and also the concept of to check the existence of limit at the function of two variables. Then what is the solution? What is the process? You see, solution. Here function is this, to take this in real and imaginary part separately. Here real part is x cube minus y cube upon x square plus y square. This is real part, taking I as a common, plus I times imaginary part x cube minus y cube upon x square plus y square. This is the value of function. This is the value when z is not equal to 0. This is equal to 0 when z equal to 0. If we compare this with the standard form of the complex function, so here we get u is x cube minus y cube upon x square plus y square, and v is x cube. This is x cube plus y cube, there minus plus x cube plus y cube, right? And first is x cube minus y cube, x cube plus y cube upon x square plus y square when xy is not equal to 0, 0. And also fz is 0. So from here u is 0 and v is 0 at xy 0, 0 at origin. Now first we have to show that if this function satisfies CR equations at z equal to 0. So here first we have to calculate the partial derivative of u and v, because we know that CR equations, that is del u by del x equal to del v by del y, del u by del y equal to minus del v by del x. These are the CR equations of any function in Cartesian form. So first you have to show that if this function satisfies these CR equations at origin, at 0, not generally. So at origin, so here we have to calculate the partial derivative of u and v with respect to x and y at point 0, 0, right? So first we have to calculate at z barabar 0. At z barabar 0 means at xy barabar 0 equal to 0, 0. So first, by definition of first principle, del u by del x is limit h tending to 0 u of 0 plus h 0 minus u of 0, 0 upon h, right? In introductory lecture, I used this. I told you about the first principle of the derivative. If the limit on the right hand side of this equation exists, then we say that del u by del x exists, and since we say that partial derivative exists, then what is the value of this? Calculate this limit h tending to 0. So from here, u of h0 means here you put x equal to h and y equal to 0. So we have x cube 0 h square plus 0 square. u0, 0 is given 0 upon h. H square is cancelled out. Finally, we get 1. Means partial derivative del u by del x exists and its value is 1. Similarly, we calculate at 0, 0 del u by del y. Then formula is del u by del y is limit, take another constant k tending to 0, and here u of 0, 0 plus k minus u of 0, 0 upon k. Right? Now again, from here calculate the value of u at x equal to 0 and y equal to k. That is 0 square minus k cube upon 0 square plus k square and u 0, 0, 0 upon k. So here we calculate and we get minus 1. K square cancel out, k cube we get minus 1. Then del u by del y also exists at 0, 0 and its value is minus 1. Now then similarly we calculate del v by del x. Take formula, limit h tending to 0, v of 0 plus h 0 minus v of 0, 0 upon h. Here, when you put the value h tending to 0, here we have the value of v is s cube plus y cube upon x square plus y square. So here we put x equal to h and y equal to 0. So here we get h cube, 0 cube, h square, 0 square, 0 upon that. So again calculate this, h cube is cancel out. Finally we get 1. That is again del v by del x exists. Similarly calculate del v by del y. That is limit k tending to 0, v of 0, 0 plus k minus v of 0, 0 upon k. Now this is the value of v. Substitute again x equal to 0 and y equal to k. That is limit k tending to 0. This is 0 k cube upon 0 square k square minus 0 upon k. Again we get 1. Right? So we get all four derivatives. Del u by del x equal to plus 1, del u by del y equal to minus y, del v by del x equal to plus 1, del v by del y equal to plus 1. All four derivatives exist, and if we see that by CR equations, therefore by CR equations, here we have del u by del x equal to 1 equal to del v by del y, and del u by del y equal to minus del v by del x. We get this result. That means this implies that fz satisfies CR equations at z equal to 0. This is the part of this is the answer of the first part of the question. The given function is satisfying CR equation at origin, but it is not sufficient for analyticity of the given function. So second part of the question is function is analytic at origin. So we have to see that at origin function is differentiable or not. Because at that point, I defined the analytic function in last lecture. A function is analytic at a point if it is differentiable not only at that point, but also the differentiable at the neighborhood of that point. So in neighborhood, due to neighborhood, function satisfying CR equation. But for the function analytic function, here we have to check if function is analytic, function is differentiable at point 0 or not. If function is differentiable at point 0 and function satisfying already satisfied, then we say that function is analytic at point 0. So in second part of the question, here we have to check whether function is differentiable at origin at z equal to 0. We have the function, what is the function? Z equal to x cube 1 plus I minus y cube 1 minus I x square plus y square when z is not equal to 0 and this is equal to 0, z equal to 0. Now we have to check the differentiability at z equal to 0. Again we use first principle. By first principle f dash 0, if we this limit z tending to 0 fz minus f0 upon z. That is the formula. You know that is the formula by first principle of the differentiability. Now we calculate this limit on the right hand side of this equation. If this limit exists, then we say that f dash 0 exists, and then we say that function is differentiable at point 0. Now calculate this limit. You know that limit z tending to 0, fz is here s cube 1 plus I y cube 1 minus I upon x square plus y square. f0 is given 0 upon z. Z means x plus I. And this is again limit of function of two variables. In our previous lectures, I told you that whenever we get the function of two variables and we have to check the existence of limit, then our method is different. Now we cannot take the left hand limit and right hand limit, but we have to calculate the values of limit along various paths. If value of limit is independent of path, then we say that limit exists. So we take path. First, we take limit z tending to 0 along y equal to mx. This is the standard part, and this is called, you know, that radius vector. If we take this path, then z is equal to, means you are putting y equal to mx, so z equal to x plus I mx, or when z tending to 0, then x tending to 0. Then this limit is f dash 0 limit x tending to 0, x cube 1 plus I minus m cube x cube 1 minus I upon x square m square x square I times this upon x plus I mx. Right? Now calculate this. If you see that, so we can take common s cube in numerator. Take common s cube in numerator, we get 1 plus I minus m cube 1 minus I. In denominator, because it shifted into denominator, we again get s cube as a common. Here we get 1 plus m square, and here we get 1 plus I. S cube is cancelled out. If you take limit, we get 1 plus I minus m cube 1 minus I upon 1 plus m square 1 plus I. Right? This is the value of limit. Now, what is the statement of existence of this limit? Whether it exists or does not. So you see what is the value? So this value is depending of m. Depending of m means not unique, because m is an arbitrary number, so it is not unique. That means does not exist. That means fz is not differentiable at z equal to 0. Right? Means final calculation we conclude that now the function here, given function is satisfying CR equation at 0, but function is not differentiable at equal to 0. So finally we conclude that fz is not analytic at particular point z equal to 0, because function is not differentiable at particular point. All those CR equations are satisfying. Now, some question may be arised by your side. You say that a CR equation is necessary and sufficient condition for a function to be analytic. Okay, but at particular point, we have to see by the definition, function is differentiable at a point as well as in the neighborhood of that point. So due to this property here, function is non-analytic. Okay, and thank you. And now in next lecture, I will continue other properties of the analytic function, in which first I will take the harmonic function, conjugate of harmonic function, and then lastly, what are the method to construct an analytic function. Means if real and imaginary part are given, or sum of their real and imaginary part are given, difference of real and imaginary part are given, then how you can construct an analytic function. Okay, thank you.